All right, the next part of this section is a discussion of rational functions. Now, rational functions are functions which can be described as a polynomial divided by a polynomial. And the name comes from rational numbers, which are described as integers divided by integers. So, for example, a rational function I can really think of as being any old polynomial. Let's just make something up here. Plus 1 divided by, I don't know, x cubed minus 20x squared plus 5x minus 3. And boom, there we go. You have a rational function here. So polynomials are much more complicated than linear and quadratic functions, and allowing ourselves to divide by a rational value just adds to the level of complication. But we're going to break it down, and similarly to the way we broke polynomials down in terms of long-term and short-term behavior. So long-term behavior is what happens as the x gets closer to positive or negative infinity here. Now, what we learned about polynomials was that the long-term behavior is totally determined by the leading terms. So x squared plus 10x plus 1, for example, is totally defined by x squared. And x cubed minus 20x squared plus 5x minus 3, its long-term behavior is totally defined by x cubed. So in general, if I want to understand the long-term behavior of any rational function, I should just take a look at the leading terms of my two things. So let's cross that out and just maybe take a look at that. So, oops. So here, ignore this thing for now. We're just looking at the long-term behavior. If I zoom out, I notice that as x gets big, the whole thing gets small. And that goes for either the positive or the negative direction. And really, this is because my q of x's behavior, if I look at the squared and the cubed, that all cancels out to be really the behavior of 1 over x, right? That's exactly what's happening here. And 1 over x, as x gets bigger and bigger and bigger, 1 divided by that gets smaller and smaller and smaller. Whether or not x is big positive or big negative, that still happens. So whenever you have a denominator that's bigger than the numerator, it doesn't matter how big either one is as long as the denominator is bigger. So I have x to the 100 and divide that by x to the 102, well, it still goes to negative infinity or to 0 in both directions. And that's because this is the same thing really as 1 over x squared. Now if the top is bigger, so let's say maybe x to the 103 over x to the 102, then everything cancels and this just has the behavior of x. So when the bottom is bigger, they both go to 0. When the top is bigger, it just goes to whatever the cancellation goes to. So this cancellation is x. If I made that x to the 104th over x to the 102, then that's the same thing as x squared. And you get whatever behavior that monomial term would have had. And if they're the same, well, yeah, x to the 104 over x to the 104, that goes to 1, right? Because when I delete both of those things, that cancels out. And so these lines are the same. And if I throw some coefficients in front of these terms, so I want to wonder what 2x to the 104 times 3x to the 104 is, it's not hard to see that that would be 2/3. So again, for the long-term behavior, we just take the leading terms reduce that to its lowest form. If the top is bigger, then it behaves like a polynomial. If they're the same, it's some constant. If the bottom's bigger, they go to zero in both directions.